Alright, in the previous video, what we did was we looked at kind of a review of what Ptolemy did with the epicycles, the eccentric, and the equant, and then we looked at Copernicus's problem with those things. 1500, well, not quite 1500 years later, but pretty close. 1400 years later was when Copernicus started working on this. And what he wanted to do was consolidate, because so many different astronomers had so many different models, consolidate it to be one model in reflection of the one true reality. He wanted to simplify, and he wanted to use the same principles of motion consistently. If you have circles, you want uniform circular motion. So what Copernicus did was first of all, he eliminated the equant. So he said, absolutely not. These planets are going to move in uniform circles, the same linear speed around the circle the whole time. He ended up using circles just like Ptolemy did, because once again, the circles were the perfect shape. You can't do better than circles. And there was still the prevailing idea that these planets and these orbits were heavenly. They were holy in some sort of a way. One thing that he didn't really want to do, but he ended up having to do in order to make the model about as accurate as the Ptolemaic models were, was he ended up having to use more epicycles. Now this went against the whole idea of models being too complicated, which was a big problem in terms of his model being better. But he also did something that was really a hindrance to the acceptance of his model, and that was to make the Earth spin and revolve around the Sun. Because, as many of you probably know already, the Copernican model is a heliocentric model. It's not the first heliocentric model that anybody came up with. Aristarchus of Samos came up with the first recorded one, documented one, back in the BCs. But this was the first modern and complete heliocentric model, and he made the Earth spin and revolve around the Sun, and we'll talk about the problems with this. The other thing is he had to put the stars really far away. Now the people at the time knew that the stars were far away. They understood this, but we're talking really, really far away. Inconceivable distances far away. And the real kicker was that his model wasn't actually better than Ptolemy's in terms of predicting where things were going to be. So it had some advantages, like getting rid of the equant, some disadvantages, like using more epicycles, some really big disadvantages like these two, which we'll talk about in more detail later on, and it wasn't actually any better than Ptolemy's model. Now, Copernicus was a pretty smart guy. He was also deeply religious. He didn't think that what he was doing was contrary to anything, any sort of religious doctrine, but he was aware that other people might. So what he did was, in the preface for his paper, he made clear that all he was trying to do was make a mathematical theory and not a reflection of the physical truth of the situation. He didn't want anybody to think that he really believed the sun was in the center of the universe. He was just kind of saying, hey, look, I was playing around, and I thought, what if we just threw the Earth out of the center of the universe and put the sun in there instead? Just a little swap. And we'll see what it does mathematically for us. See if we can get a simpler, easier to use model. And he got away with it, because he claimed it's not really a reflection of the physical truth. Now, for Copernicus's contemporaries and then the people following, there were four major problems, I would say, that either the Copernican model or the Ptolemaic model had to address. They had to do it. Otherwise, you couldn't really consider them a complete model. One of the things, retrograde motion. There's also something called parallax, which we'll talk about, varying speeds of orbits, and the rotation of the Earth. And we'll start with the retrograde motion. So, first of all, here it says Ptolemy used epicycles, equants, and eccentrics. That's how he pulled off the whole retrograde motion and also the varying speeds of the orbits, in addition to the forward and backwards motion. Why does it go so fast sometimes and so slow other times? And with the Copernican model, the heliocentric model naturally accounted for the retrograde motion, at least qualitatively. If you look at it qualitatively, heliocentric should have done the trick. However, it didn't quite work. So Copernicus still ended up having to use epicycles in order to make it work out completely. I'll see if I can show you this. Okay, so here we have kind of an off-centered picture, but good enough. This is the Earth, this is Mars, and the Earth goes faster than Mars does around the Sun, according to the Copernican model. And so what we would have then is that, and I did a poor job of drawing both of these arrows actually. So let's say that this is the Earth's speed at that point, and this is Mars's speed at that point. That means that the relative speed of Mars compared to the Earth would be backwards. Meanwhile, the stars would be orbiting around at a certain speed as well, or you could claim that the stars were fixed. So, depending on how you work with the stars, it depends on exactly how you see this, but from Earth's perspective, Mars is going backwards when Mars is located right here. On the other hand, if we put Mars on this other side, which you'd get to this arrangement at some point in time, so you'd have Mars still traveling along at its slightly sluggish pace, and you have the Earth still in this position over here, so we'll just draw it like this, and you have Mars going this way instead. Well, that means that in order, or from Earth's perspective, Earth sees Mars traveling this way at a really high speed. And this would be sort of the normal way that something on this side would be traveling, would be spinning around. So right now, this would equate to Mars really rapidly jumping forward. This would equate to Mars going backwards compared to everything else. So if everything is kind of spinning in this direction in the universe, Mars is getting a leg up on it here. Mars is kind of going backwards the wrong way in this case. So we have this sort of a retrograde motion type of idea built in to the heliocentric model. The only downside is that it didn't work. And qualitatively, it works. It makes sense. You've got varying speeds just built into this model. You don't have to do anything special. You don't have to put epicycles in there. You don't have to put things off-centered and so on. It just works. The problem is that it just works for a different solar system, let's say. It didn't work for our solar system. So in spite of the brilliance of the model in terms of qualitatively explaining the retrograde motion, because it didn't actually work, Copernicus still needed to use epicycles. And actually, because he got rid of this, primarily, he had to make a lot of adjustments using more of these. So it was kind of a wash. It seemed like a great idea. It should have worked pretty well, but in practice it didn't quite work out. But some people felt that this, even though it didn't work out as well as we had hoped, the fact that it sort of naturally explained that retrograde motion was a plus for some people. Parallax was another issue. To explain parallax, let's just look at this particular case. This would be the Earth, let's say, orbiting around the Sun. And if you have stars that are fairly close to the Earth, or even planets that are fairly close to the Earth, then what you're going to notice is that if you're observing from, let's say this is spring and this is fall, if you're observing from the Earth during the spring, and you're observing from the Earth during the fall, what you'll notice is that there's a different background of the stars behind an object that's the same position compared to the Sun. You would notice a different background. And you can do this for yourself by taking your finger and holding it pretty close to your face and closing one eye and then closing the other eye and looking at something behind your finger. And you notice that the things that are immediately around your finger in your viewpoint change if your finger is close to your face. As you extend your finger further and further away from your face and you do this eye switching, you'll notice that the background still changes, but not nearly so much. And that would be like this small parallax angle picture, where everything is located pretty far away from the Earth. And as a result, we don't notice a parallax. And the issue is that we didn't notice a parallax. We didn't have tools at the time to actually notice any parallax between anything that was out there. Now, Ptolemy accounted for this lack of parallax pretty easily. He just said, you know what? We don't need to worry about parallax. It wasn't even an issue because the Earth was unmoving, and it was in the center of the stars. So the stars were just rotating around the Earth. The Earth wasn't moving. You were never changing your perspective. So the result was that the stars always looked as if there was no parallax. And that was just natural because you weren't changing your observation point. Copernicus recognized that he was changing the observation point of the Earth, and as a result, you would get parallax unless nothing was very, very close to the Earth in terms of the stars. All the stars were far away. So he had to put the stars really, really, really far away. And it was so far away that it made the model improbable to many people. The distances were too great to conceive of. Nowadays, we would look at it and say, well, yeah, he got it about right in terms of how far away they were. Actually, he didn't get it about right. They're even further away than he could have conceived of. But they had to be basically almost infinitely far away, and they are. So that's another of the issues that the models had to account for. And once again, Copernicus, he had some good ideas, but it just seemed so wrong by the contemporary thinking of the day. So that was a huge problem. We'll pick up with the other ones in the next lecture, or I'll go over them in class.